want to think about as you look at this image is picture all these random events, the changes to the environment, and changes to the phenotypes of organisms as being kind of like a constant rain falling down on this whole phase space diagram. And just as rain would be channeled down into the channel or the valley and flow along, in a similar way, you see how natural selection, which is anything but random, channels the mutations very efficiently through phase space. Once in a while you have a few organisms, see a few dots up here in the valleys, the foothills. They're just barely making it up there. They're not very well adapted. They don't survive very well. And up here in the taller mountains, nothing makes it up there. Okay, so the principles here are that the number of organisms at each locus in phase space builds up until the probability of the next step becomes inevitable. There's the principle that one step leads to another. By many small steps you can climb a mountain, and by many small steps a dramatic change in organisms can occur over evolutionary time. Notice that evolution leaves behind what I call a trail of ancestors. See, look at that trail of all the ancestors that are still there, still beautifully adapted to their respective environments. In my class, someone always asked me, Dr. Rainbow, if humans have evolved from apes, they always think humans have evolved from apes, which they haven't. We've evolved from ape-like creatures. But they say, if humans have evolved from apes, why are there still apes in Africa? I always get that question every semester. And you should be able to easily see now that that's an exceedingly silly question. That's no different than asking, why are there still fish 5 miles below the surface of the ocean? What's the answer? Because they're beautifully adapted to their environment. Another principle is that evolution is a blind, random, fluky process driven by random mutations to DNA and random changes to the environment. Well, I already said that. It's, the selection is anything but random. So in a supreme irony, this process, as I hope you may be able to see, even though it's driven by random processes, it ends up creating creatures that look just as if they'd been designed by a creator. Which they really have, haven't they? Because it's the creator who dictated Le Chatelier's principle, and Coulomb's law, and Newton's second law, and the Schrödinger equation, and all the laws that govern how the atoms and molecules self-assemble. So God still gets all the credit for this. In fact, he's an even more awesome God. Now, let me take stock of where I am. How many minutes over am I? 5:45. Okay, I mean over my time. What? Oh, 5 minutes. Okay. Because I need to respect the interplay that you've all come to see. So give me a second here to decide on how I want to use my time. I actually almost finished what I needed to there. Okay, what I'm going to do is simply make one last titanically important point about evolution. Now, what is it that you're all wondering the most about? This all makes a lot of sense. We know that this happens. Creationists freely admit that evolution takes place. They would say, however, that only microevolution can take place. I have no doubt at all that Dr. Hovind would agree with the fundamental essence of this picture, but he would say that you can only get small changes to organisms, like changing one insect into a different color or something like that. That's called microevolution. What you're wondering is, can you really go from things like a fish to an amphibian? Can you get big time evolution, big changes, big dramatic changes, which is called macroevolution? And what I'm going to do here is try to explain the results of the field that I at least like to think of as my specialty, and which is called EVO-DEVO, or Evolutionary Developmental Biology. And I'm going to show you some animations that show how you can create radically new forms of organisms incredibly easily. All right, so I need to close this and open up this one. Okay, this is an animation I use in my class. Oh, let's see, did that open? No. Okay. I got too many things to hold here. Put it on the whole screen. Okay, living things are made of cells. And you have to understand that during embryological development, living cells can do 7 different things. They can divide by mitosis, cell division. So things can get really big really fast. They can differentiate. They can turn into different kinds of cells. Like here, 2 initially identical cells are turning into muscle cells and neurons under the influence of a morphogen that's being sent by this cell. They can crawl around. Cells can crawl around anywhere at any time in your body, just like amoebas do. They can lay down extracellular matrix like big strands of collagen. They can change their shape. Here you see a cell in the middle changing its shape. So this epithelial sheet is buckling and folding. It's like making a paper airplane. One of the things I do in my class is I take out a piece of paper, and in front of the students, I step by step make a paper airplane. And then at the end, I hold it up and I say, look what a complicated thing I made just by doing one thing, folding paper. I take a piece of clay that looks like this, and I cut it with a knife, boom, 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 and I make a hand. Did you know that your hand got here you used to have a paddle like a duck. You had flesh in between your fingers, and then your cells here died by a process called programmed cell death, or apoptosis, which generated your fingers. That's another of the things that they can do. Cells can commit suicide at any time. And they can attach together or break apart at any time by expressing cell adhesion molecules. So, with these facts in mind, we go to another animation, which I call infinite outcomes animation. And here we have 5 different subdivisions of it. In the first animation, we're going to see how cells can divide and differentiate, and just look at how fast things can get complicated. Okay, they're dividing. You have 2 kinds of cells, blue and yellow. See, there we made something fairly complicated just by going through a few rounds of cell division and differentiation into only 2 types of cells. You have more than 200 kinds of cells. Okay, and then the second animation is an example of what